Coronal mass ejections from the sun are perhaps the most dangerous threat you've never heard of. Also known as solar storms, they hurl large masses of supercharged particles across 93 million miles of space. Most take several days to travel from the sun to the Earth, but some rocket across the solar system at up to 6 million miles an hour, reaching our planet in less than 16 hours. These storms can induce currents in the outer atmosphere, knocking out satellites and cross-country power grids, and carry the potential to wreak just as much havoc on our infrastructure as a hurricane or tornado. But who on Earth is keeping an eye on these potentially hazardous cosmic blasts? This is the headquarters of the National Oceanic and Atmospheric Administration, home to the U.S. government's National Weather Service. Their daily forecasts, watches, and warnings are essential information for everyday life on our planet. But there's a lesser-known group of forecasters working here in a special division called the Space Environment Center.
Our primary job is to monitor the sun and to put out the alerts and watches and warnings for solar activity.
Good morning, welcome to our 810 briefing. We had one long-duration C flare from the east limb. That's possible CME. We have not had protons, but we have had electrons.
One thing to note is that this region produced all the activity in December, so things might be picking up here in the next couple of weeks.
These space forecasters are on high alert for solar storms that might disrupt life on Earth. Solar storm clouds are made up of charged particles, so they're initially diverted around the planet by our magnetic field, just like waves breaking around the bow of a boat.
That turns out to be very important because if it impacted the outer atmosphere directly, it would knock little bits of the atmosphere off into space. One reason why Mars doesn't have an atmosphere is that it doesn't have a strong internal magnetic field. And so gradually, over millions or maybe billions of years, the atmosphere was gradually knocked off into space by the influence of the solar wind and by CMEs that came past the planet.
But our magnetic field is not the perfect force field of sci-fi movies. Some particles can penetrate it, charging up the upper atmosphere. Solar storms will even bend and break the magnetic field lines on the far side of the Earth, allowing charged particles to zip back down the field lines toward the north and south poles. Extremely powerful storms distort the magnetic field even further, inducing electric currents that span the continents. When this happens, technology like long-distance power lines can become overloaded.
If we have that storm that hits our communication system, it hits our power companies and all these things that we depend on, there's all kinds of chaos that can lay out there.
If power operators have time to react, they can reduce the current being sent over their wires and avert disaster. Satellite operators can also prepare for the onslaught with proper warning.
When there's a big space storm coming, they'll actually put some of their satellites to sleep so that the storm doesn't cause an electrical short or otherwise somehow knock out the satellite. So the more warning time they have, the better.
We wouldn't go sailing unless we knew what the weather was going to be. Similarly, when we have a large system like a power system or a telephone grid that can be affected by the weather in space, we need to know what the weather is going to be so that we can try and mitigate it.
Solar storms can also disrupt high-frequency radio communications used by aircraft. In the 1980s, Air Force One was transporting President Reagan on a trip to China when a solar storm struck. All communications were lost for several hours, effectively severing the head of the United States government.
The urgency is just like our Earth's weather. When we have a tornado warning, we know the urgency to get that out to the public, to let people know that this is happening. The same thing is with space weather. Users of this information need to know it, and they need to know it now. Just a few hours back, we experienced a coronal mass ejection. We want to see where this blast is going out, and then we can measure that and see how long it might take from that to reach the Earth from the sun. We're seeing a very huge explosion of material that's coming out, and if you look at this small image here, here's the sun that's covered up, and look at the mass that's being thrown out into space. So it's huge, very huge.
Because magnetic field lines emanate from the north and south poles, energy from solar storms has easy access to those regions. For that reason, experts worry that airplane passengers flying over the poles during a powerful storm might be exposed to harmful levels of radiation, perhaps a dose equal to 100 chest X-rays.
It's not something that we want to mess around with, because we never know when that radiation might all of a sudden become a lot more intense while there's an airplane in the sky.
The threat from solar radiation is just one more reason scientists keep a close watch on our sun.
It matters, especially in modern times, what the sun is doing. Earth is not an island. We are a participant in the activities of the solar system.
Sunspots are the triggers for most severe solar storms, so forecasters track them carefully as they rotate across the surface of the sun.
Location, location, location. We see coronal mass ejections all the time from the sun. A lot of them are as the sun is rotated around or from the backside of the sun. That would not be faced toward the Earth, so that would be less of a concern. As the sun rotates around and that active region gets more into the center of the disk, looking at us, then that's when we would be concerned with. From the center of the sun, as it rotates around, is the kill zone.
As the sunspot rotates around and begins to face directly at Earth, that's when we really have to worry about a storm. If a big storm lifts off then, it can aim directly at Earth and the full force of the storm slams into the planet.
It's like a shotgun aiming at a target. The more dead on the shot, the more likely serious damage will be inflicted. With great danger also comes astonishing beauty. Solar storms generate majestic planetary light shows, the shimmering curtains of color called the aurora. Auroras work like neon signs on an enormous scale. In a neon sign, electricity introduces charged particles into a gas-filled tube. The particles in the gas are excited and start to glow. If the tube has only neon inside, it will glow red. By adding other gases, like argon, a whole range of colors can be produced.
The neon sign is driven by the electric field inside the tube, whereas the aurora is actually driven by the magnetic field and energy from the sun.
As the energetic particles in a solar storm stream along Earth's magnetic field towards the poles, they excite elements in our atmosphere, causing them to glow. Oxygen molecules emit a green or red color, and nitrogen emits pinks, blues, and violets. While these ghostly lights are usually confined to the poles, extremely strong solar storms can drive them closer to the equator. In 1859, a geomagnetic storm ignited by a huge solar flare created auroras as far south as Rome. The 1859 storm was an unusually powerful event that some have called the perfect solar storm.
The 1859 storm taught us a little something about what the sun can do. The storm was so intense and the alignment was so perfect that it simply overwhelmed Earth's natural defenses.
A huge solar flare erupts on the surface of the sun. Less than a day later, and 93 million miles away, the wires that carry communications across the Earth begin to spark. business grinds to a halt worldwide as wildfires are ignited by the smoldering lines. At the same time, colorful auroras light up the skies of cities around the globe. Earth has just been visited by the perfect solar storm.
The sun kicked up this just incredible solar flare and a massive amount of energy headed towards Earth.
Not only was this storm one of the two most powerful on record, it was also one of the fastest. Ejecting from a sunspot aimed directly at Earth, it raced from the sun to our planet in less than 18 hours.
Now it takes a really fast rocket ship years to get to the sun. This storm, this cloud of electrified particles, managed to get here in less than a day. That's incredibly fast.
Fortunately, the perfect solar storm took place in 1859, when the only technology vulnerable to the onslaught was the telegraph. Since the era in which we have become dependent on high technology, we've yet to see another perfect solar storm. The question remains, could it happen again?
What if we have another one like that? Can we have another perfect storm? Well, I'd say yes, we can. There's no doubt about that. The effects that would be on us today compared to 1859 could be devastating.
The effects on Earth and on our communication systems, we don't exactly know. That's the scary part.
It's likely that our modern technologies would be battered like beachfront houses during a hurricane. Imagine if we lost all the satellites that relay cell phone calls, television signals, and bank transactions. And what if, at the same time, the failure of power grids cascaded whole regions into darkness for hours or weeks? If these essential services couldn't be restored quickly, chaos wouldn't be far behind.
It would definitely be a ripple effect upon society and every man and woman and child that lives on this earth.
Solar storms can be as hard to predict as hurricanes. While forecasters lack the technology to foretell the next perfect storm, they do know that one would be more likely to hit at the peak of the sun's 11-year sunspot cycle.
What happens is the sun reverses the direction of its magnetic field every 11 years. So in 22 years, it reverses and comes back to where it was.
As we near the reversal every 11 years, the number of sunspots increases, and there's a spike in solar activity.
We call that period solar maximum. And those periods are interspersed about 5 years apart from periods we call solar minimum.
So you have this 11-year back and forth between the sun being sometimes very ferocious and it goes crazy and it's like the 4th of July with fireworks all the time. And then it starts to ramp down, and for a few years it gets quieter until we get to a low point where there's a firecracker now and then, but not a lot going on.
Just like hurricane seasons, solar maximums vary in intensity. Some produce many more powerful storms than others. Although we're currently at solar minimum, scientists are watching carefully to see what mayhem the next solar max might unleash.
So the last solar maximum was in about 2001, and so the next one ought to be about 2012. But there are different predictions. The whole field of solar physicists is basically waiting with bated breath to see what actually happens.
There are some wildly divergent opinions on what's going to happen. One group is suggesting that this next solar cycle could be the strongest in modern times.
If those predictions are correct, Earth could be in for a wild ride.
We might have to worry about a repeat of the 1859 event. If that were to happen today, it would wreak untold damage.
We're going to learn a whole lot about what can happen to modern technology when the sun blows its top.
Much of the violence in the sun erupts here, in the hellish outer atmosphere known as the corona. This region has long held one of the great solar mysteries, because even though it's 500,000 miles from the heat-generating core, it burns at millions of degrees. This seems to violate the very laws of physics.
That's very strange. I have a thermometer here. If I hold the thermometer close to the fire, it reads a very high reading. Where the probe is right now, it's over 200 degrees. Now, if I pull the probe out a little farther from the fire, okay, it drops down to about 90 degrees. Now, the farther I get from the center, the cooler it gets. In the atmosphere, the corona of the sun, the temperature soars as hot as the core. That's as if I were to say, well, way off behind me there, the heat from the fire is as hot as the fire itself, even though it's very far from the fire.
What force could possibly cause the superheating of the corona? The answer will rock you. The hellish solar corona rages at millions of degrees. For centuries, scientists have been baffled how anything so far from the sun's core could still burn so hot. Recently, as improved satellites offered a closer view of the solar surface, clues began to emerge. Below the corona, the sun's surface is literally boiling.
The reason is that the entire surface of the sun is covered with convection cells, hot material from the inside of the sun. It rises up through, reaches the surface, cools off by glowing, giving off sunlight, and then sinks back down. Each bubble of material that comes up is about the size of Texas. It spreads out across the surface, cools off, and sinks down in 5 minutes. So that's a tremendously violent process. Well, that's happening in literally almost 1 million places over the entire surface of the sun all the time, around the clock, 24/7.
This boiling isn't only violent, it's also extremely loud.
The sun is a tremendously loud place. If you could imagine covering the entire surface of the sun with speakers being driven as hard as the loudest rock concert you've ever been to, that would be comparable to how loud it really is on the surface of the sun.
The sun's churning surface creates enough sound energy to superheat the corona to millions of degrees. Scientists believe that a combination of these sound waves and energy from the sun's magnetic field is responsible for the extreme temperatures found in the corona. The only time you can actually see the corona from Earth is at the climax of one of the most dazzling displays in the solar system, a total solar eclipse. Before scientists understood them, these awe-inspiring events instilled only fear. The ancient Chinese believed that a dragon was devouring the sun. So what's really happening in a solar eclipse? In simplest terms, it's when the moon blocks our view of the sun.
Imagine that you're sitting in the movies watching very happily something going on the screen, and then somebody in the row in front of you comes across and blocks your view. In the movie theater, you might not want that person to come across in front of you, but at an eclipse, we're very lucky to have the moon come across the sun, and we're lucky to have it come right across the middle.
We're also lucky that the moon, although it's 400 times smaller than the sun, is also 400 times closer to us. This cosmic coincidence means that the two objects just happen to be the same apparent size in our sky, which allows for one to completely block out the other. This magnificent cosmic event only happens when the path of the moon intersects the line between the Earth and the sun. The moon's orbit is tilted slightly, about 5 degrees. If it wasn't, we would have an eclipse every month.
And then we'd be bored. But we're not bored because most months the moon goes above or below the place where the line goes from the Earth to the sun.
So instead of one every month, we get a total eclipse somewhere on Earth about once every year and a half. As the moon slides in front of the sun, it casts a shadow onto the Earth. The outer part, where the shadow is fainter, is called the penumbra. If you're standing within the swath traced by the penumbra as it moves along the Earth's surface, then you'll see only a partial eclipse. But travel to a spot within the path of the dark inner shadow called the umbra, and you'll experience the majesty of a total eclipse. There's another option if you can't travel to the path of totality. Wait in one place long enough, and a total eclipse will pass right over your head about once every 300 years. The sun, that shining star of our solar system, is capable of both astonishing beauty and ferocious violence. It seems impossible to believe, but it won't be around forever. Eventually, even the sun must die.
The sun has a fixed amount of fuel in its core. It is undergoing fusion at a rate that you can calculate. You say, here's the rate it's using its fuel. Here's how much fuel you have. So it's a simple calculation to show when the sun will die. And that's in about 5 billion years.
Well, unfortunately, the sun will not go out with a bang. It is too small to erupt in a supernova. However, stars do a peculiar thing. They're one of the few things around that get hotter as they cool off.
As it exhausts its hydrogen fuel, our nearest star will cool and gradually collapse under the force of gravity. Energy from this collapse will start heating up the core again to hundreds of millions of degrees, hot enough to start burning helium. Under the extra heat of the helium burning, the star will expand into a monstrous orb called a red giant.
It gets so big, it will engulf the entire orbits of Mercury, Venus, and Earth. You don't want to be around for that. You want to be planet hopping your way to safety long before this happens.
The Earth is likely to change its orbit slightly as the star expands so that it won't be engulfed. Still, talk about global warming, you wouldn't want to be there.
The outer layers of our sun will eventually become so unstable that they will fly off into space, leaving behind a small core about the size of the Earth.
So remember, we've shrunk most of the sun, which is 1 million miles across, to the size of the Earth, which is more like 6,000 miles across.
Our once great star reduced to a slowly cooling cinder.
And life as we know it on Earth will cease to exist. And that is the death of the sun.
All of this is bad news for the human race. But look on the bright side.
We've got 5 billion years to prepare for this disaster.
For now, humanity basks in the glow of a sun in the prime of its life. Science has uncovered